Hey guys, so I'm going to go over how we calculate a hypothesis test for a mean difference. And so remember, for a mean difference, that is where we are pairing up individuals from two different populations, and we're finding their individual difference with each other and then finding the average of all those differences. So when we think about the example of doing a group of juniors and a group of seniors in a mean difference example, I would pair each of you up with somebody from the other grade. You would find your difference between the two of you, and then I would collect the data on all those differences and find the average from there. And so what happens is now we have a one sample test, even though we have two different populations that we are trying to relate to each other. So we are picking back up with the context that we did in the last unit when we did a confidence interval for mean difference. And that is, we are going to suppose, or it's about climate change. So suppose that 32 weather stations were randomly selected across the globe. Right away, I see a potential N, right? Our sample size, we selected 32. So I'm going to highlight some important things as I read, show you what you should be doing as you answer questions as well. So for each station, the peak annual temperature, degrees Celsius, between 1900 to 1940 was found. So that looks like our first population, right, being between 1900 to 1940. Then the peak annual temperature between 1960 and 2000 was found. So there's our second population. The differences were calculated for each station. So each station individually, we paired up their early years and their later years, and we found the temperature between. And I'll put that here, actually. Later temperature minus earlier temperature. The mean of the differences was x bar sub difference equals 0.35 degrees Celsius. And the standard deviation was S sub difference equals 0.296 degrees Celsius. Do these data provide convincing evidence that the peak global temperatures increased on average during the 1900s? And I'm going to highlight this in a different color because this last sentence is really important. It is setting up the context of our whole problem, like what it is that we are truly testing. So as I get ready to begin this problem, I'm going to make sure that I do every part of state plan do conclude, which is set up for us in this example here. So starting with state, we're going to state our parameter. And for the parameter, we are looking at the symbol mu sub difference. So remember, our parameter is the population mean. And here, because we're doing that paired test where we're pairing the earlier years and the later years from the same station, it is mu sub difference. And what this is in context is the true mean differences of peak temperatures and that is the late minus early as it's set up in the problem, but we still want to make sure that we are defining the direction we're using as well. The statistic is given to us straight from the problem. That is our x bar sub difference, and it is 0.35. The significance level is not explicitly stated, so we're just going to assume the significance level of 0.05. And now we want to write our hypotheses. So starting with the null hypothesis here. For a mu sub difference, it still is a difference between two different samples. And so we write it a little bit differently, but still we are testing to see against the null hypothesis that there is no difference. So our null, what we are going to assume is that this mu equals 0. Then the alternative, that's what we think is going to actually happen. We believe that there should be an increase, that when I do the later years minus the earlier years, the later years will be larger than the earlier, and therefore when I do late minus early, this difference should be greater than 0. All right, now moving on to the plan phase. This is a one sample test because even though we have our two different populations, we are pairing them up and we are only focused on the sample of differences. So we call this a one sample t-test for mu sub difference. And this 4, whatever comes after 4, that's always going to be whatever symbol you used for your parameter. All right, so checking the conditions, I'm going to check our 3, the first one being random. And if I reread the problem, it does say that our 32 stations were randomly selected. So I'm just going to say 32 stations randomly selected. And as we write these conditions, I would just want to remind you of like the reason why we check each one. So like, why do we check a random condition? What does the random condition allow us to do? Well, this is so we can generalize our results to the population. So to the population of all stations for this specific example. All right, the next one is the 10% rule. So is 32 less than 10% of all stations? And yes, it is. And remember, why do we test this 10% rule? The reason is so we can, or so sampling without replacement is okay. So when we sampled here, we did it without replacement. We are assuming that they took 32 different stations, and therefore we would then check the 10% rule. And the last one is testing if this is normal. And so for normal, we could do 3 things. First off, if the problem told us that the population was normal, which it does not, so we can't do that one. The second one is by the central limit theorem, if our sample size is large enough, and large enough has been set at 30 or more. And if I look at this, our sample size was 32. So here, I do have a large enough sample. So by the central limit theorem, because 30 is greater than, because 32 is greater than or equal to 30. We are, in fact, normal. Now, why do we want to be normal? That is so the sampling distribution of X bar difference is approximately normal. And this is so that we can do the problem using a normal distribution or that t-distribution. All right, moving on to the do section. Our general formula has not changed. It is test statistic equals statistic minus parameter over standard deviation. The specific formula now is T equals, our statistic is X bar subdifference, minus the parameter is mu subdifference, over the standard deviation. Well, here remember from our formula sheet, that the standard error for these problems is the standard deviation of the sample over the square root of n. But now we're doing the standard deviation and n of this difference. So it's the standard deviation of the difference over that square root of n. So for my work, I can plug in T equals for X bar subdifference. We know that that was given in the problem as 0.35 minus mu subdifference. Remember, we always assume that our null hypothesis is true, and so that's what we use as mu subdifference. So minus 0 over standard deviation, again, was told to us in the problem, so 0.296 divided by the square root of n. Our n value here is 32. All right. Plugging this into my calculator, I got a t-score of 6.69. All right, so I'm going to go over to my picture. I'm going to draw a picture here. And I'm going to label my curve as t and then the degrees of freedom. Well, if our sample size is 32, that would make our degrees of freedom 31. So T31. I'm going to label the center as 0. And then I'm going to plot my t-score. So our t-score is 6.69. So I'll plot that here. And we believe it's greater than. So we're going to shade above. So my test statistic is 6.69 again. And the p-value, well, in order to find the p-value, I'm going to use my calculator. And so in my calculator, remember, I'm using the function TCDF, and I'm doing the lower, comma, upper, comma, degrees of freedom. For this one, because we shaded above, the lowest point of our shading is our test statistic, and the highest, we're just going to make a really high value, so that way it continues to the right along this distribution. So I would do TCDF of 6.69, comma, 100,000, comma, degrees of freedom 31. And when I plugged that into my calculator, I got 8.76 e to the negative 8. And if I move this over 1, 2, 3, 4, 5, 6, 7, 8, that is quite a small decimal right there. And if it is that small, then I'm going to say my p-value is approximately 0. Now, one helpful hint, when you are taking your test, your t-score and your p-value are two very important pieces of your answer. And so if you were to box those in for your teacher or your AP exam grader, I'm sure they would be very thankful for that, just that you are showing that you know what is important here in your answer. All right, so now we have our p-value. We are ready to conclude and to interpret our p-value. Erase this here. And so for the conclusion, the first part is interpreting that p-value. So I'm going to start with assuming the null hypothesis, so HO is true. And remember, that is that mu sub difference equals 0. There is a 0 probability, remember that's just our p-value, of getting an x bar sub difference, so a sample mean of 0.35 or greater, because we shaded above, purely by chance. And again, this first part here, this is us interpreting P. And I always say that this interpretation is super helpful. If you are having a hard time with understanding what a hypothesis test is, read this interpretation and really try to understand what the p-value tells us, because I think that will really help you understand how a hypothesis test works.